Hello and welcome to this video on setting up contact pairs in ANSYS Workbench Mechanical. We'll mention where it is in the help system. Note that contacts are automatically created when geometry is first brought in, that we can tweak the options for automatic contact creation. Then we'll mention manual contact settings when you want things that are nonlinear, or to adjust the linearized contact types. And we'll mention some advanced contact settings. First off, if you go into the help system, note that in mechanical applications there's a section on contact, and it discusses many topics. Within contact, you can work through them and learn many details. Here's a model that's been imported, and in the geometry you can see two concentric circles. There's a solid cylinder inside of a ring. When that geometry is first imported, some connections will be automatically created. We will get a contact pair between these two bodies. The reason for that is that this auto detection tolerance between bodies, if I go to a view straight in, you can see there's a small gap, but the distance in here is 0.32, and automatic tolerance is greater than the size of that gap. For that reason, a contact pair has been automatically created when the geometry was brought in. You can change the size of that tolerance with a slider if you wish to. You can also put a numerical value in and have explicit control over the proximity of bodies so that contact pairs will be automatically set up. I'll go back to my slider. My geometry was imported and a contact pair that you see here was automatically created. Now when it's brought in, it'll be a bonded contact, as if the things were stuck together like glue. There are a number of settings for the contact pair. You can make it bonded, that's the default. No separation, that lets the two surfaces slide over each other without friction, but they cannot come apart. It's still a linearized contact in small deflection analysis. You can request frictionless contact. They slide without friction, but they can pull apart. It's a nonlinear setting. There's rough contact, which acts as if there's an infinite coefficient of friction. They won't slide, but they can come apart. There's frictional sliding. If you choose that, you insert a coefficient of friction yourself. In this particular example, we were working with frictionless sliding. Gaps can open up, and it'll slide without a coefficient of friction. Other things to note. I've gone to a non-default setting on behavior. I've asked for asymmetric contact, so there's only one contact side and one target. The inner body has the contact, the outer body has the target. What happens is that during analysis, the software looks to see whether points on the contact side have touched the geometry of the faces on the target side. There are a variety of other settings in here. Formulation. Augmented Lagrange would be the default for how a contact behaves. That gives penalty springs when you touch to try to keep things from penetrating too much, but also brings on a pressure in order to stop penetration from being too great. You could choose a pure penalty technique, which uses spring-like effects only to stop bodies from penetrating. Multipoint constraint is to bond things together by making points, actually the nodes on the contact side, track face movements on the target. That's only for the linearized contacts, bonded and no separation. There's a normal Lagrange technique that uses Lagrangian multiplier methods to create degrees of freedom that are pressures on the contact that prevent penetration. And you can also have bonded contacts locked together with a series of beam-like connections, which might help you cope with bonded contacts across fairly large gaps when you want it to act as if the gap had been filled in by an invisible material that locks everything together. There are a variety of advanced settings. How do you detect whether you've contacted? The nonlinear effects use Gaussian quadrature points as the points on the contact side. You can work directly off nodes to see if things have touched. You could search in a direction perpendicular to the contact face, perpendicular to the target face. There's a specialized setting in here, nodal projected, normal from contact, and it takes into account how much face of an element on the contact side has overlapped how much face on a target side. That can give better results in some special situations. If you're using a penalty technique, you can play with how stiff the contact stiffnesses are. That can help with nonlinear contacts. Do you update those stiffness values according to what's happening in an analysis? If I have something like a nonlinear contact between something made of rubber and steel, I might want to update my contact stiffnesses from iteration to iteration. I can put in an artificial stabilization and artificial damping to try to cope with difficult problems. I can also play with how big the contact pinball is. That's a distance. If the contact and target are close to each other within that pinball size, detailed calculations are done to see if they're actually touching each other. There's a default here which is just called program controlled. It's often helpful though to set that radius yourself and to see that it is bigger than your gap and to see that it's big enough to take into account many nonlinear situations that might arise. Further down, I have interface treatment. Default is add offset, no ramping, which means that the surface is not offset if this number is 0, or I can specify something. It's sometimes used for interference fit work. For improved convergence, there are times when you want to ramp up that offset through substeps. In this particular example, though, I've requested adjust to touch. I want that red contact surface offset until it begins to touch the blue target surface. For that to work, the gap in here needs to be smaller than the pinball radius, which is what we have. If I go up, at the connections level, I can insert a contact tool. Here's one. That contact tool can be used to tell me about the gap in my model and to give me initial information in this worksheet format. Here I see that my original geometric gap was this 0.2649 millimeters. I see that it has been closed up by my setting adjust to touch, and we're getting a numerical round off for a slight number right here. To evaluate that, I go to Generate Initial Contact Results, and this can tell me about my contacts with the elements in their original position in space before any solving and loading is done. So here we see that we have basically no gaps. I can go down and I can solve the model. Here's my total deformation. Note that the result has been exaggerated by a factor of 2 million. That's the displacement. You can see that the inner cylinder has been pushed to the right by this force, while I hold the outer cylinder's outside diameter with fixed support, and I've put a remote displacement on the back of the inner cylinder. Have a look at what I constrained. I stopped it from moving in Y and Z, and I prevented it rotating, but I permitted it to move in the X direction, which is the direction in which I replaced this force, 10 newtons. So you can see that it displaced to the right. It's come into contact here. If I look at my stresses, I have stress out here because of the contact. I can insert a contact tool down in the post-processing area as well. There's one. In here I can look at such things as contact status. Here you see the orange sliding. That's because it's in contact but there's no friction. And on the left we're near. We're inside the pinball radius but we're not touching, as is implied by this look at the displacement. I can also check my contact pressure and see that because of the load and displacement constraints I put on the model, that's the contact pressure on the contact side for the model that I set up. One other topic, I'd like to look at the mesh. Now this is not an ideal meshing. I have coarser elements on the contact side than I have on the target, and I really should have finer elements on the contact side. So before I go, let's quickly look at a modified meshing. As a rule of thumb, the contact should be on the softer material, have the finer mesh, and be on a convex curve. If I solve again, this is still a coarse mesh for coming up with any real contact stress, but just to illustrate. There's the displacement, similar plot to what we saw before. Here's the state of stress, it's more concentrated now. So the result that I have is going to depend on the kind of mesh density that I've used. There's a quick introduction then to checking contacts and some of the possible settings. Thank you for joining me.